Hello and welcome to AI for Developers. I'm Chaitanya talking bot. Today's lesson is titled DQ Networks. DQN. Teaching AI to play Atari like a human. Imagine you want to build an AI that can play video games like an old Atari classic, Pong, Space Invaders, or Breakout. But here's the catch. You can't tell it the rules, or what buttons to press when. All it gets is the game screen as input and the score. How would it learn? This is where DQ Networks, DQN, come in. It's a groundbreaking method that taught AI to master these games, often outperforming human players, purely through trial and error, just by looking at the pixels and getting a score. For us developers, think of it as writing a program that can figure out complex strategies on its own, without explicit instructions. At its heart, DQN uses a concept called reinforcement learning, RL. Think of it like training a pet. If your dog does something good, like sitting, you give it a treat, a reward. If it does something you don't want, you don't give a treat, or maybe even scold it, a negative reward. In RL, we have agent, our AI program, the dog, trying to learn, environment, the game itself, the world the AI interacts with, state, what the AI sees right now, in Atari. This is the current screen image. Action, what the AI can do, pressing the joystick up, down, left, right, or firing. Reward, the feedback from the environment. Getting points in the game is a positive reward. Losing a life is a negative reward. The AI's goal is to learn a strategy, called a policy, to maximize its total rewards over time. As developers, we're building the framework for this trial and error learning. How does the AI decide which action is best in a given state? This is where Q learning comes in. The Q stands for quality. A Q value tells us how good it is to take a particular action when you're in a specific game state. Imagine our AI trying to build a giant cheat sheet or a strategy guide called a Q table. In this table, for every possible game screen, state, and every possible action, e.g., move left, move right, it tries to store a number representing how beneficial that action is. A higher Q value means this action is likely to lead to good future rewards. The AI updates these Q values as it plays and learns, gradually figuring out the best moves. As developers, we'd conceptually want to build a system that assigns these quality scores to actions. The Q table idea works well for simple games with few states, like a small maze. But think about Atari games. Each screen is an array of pixels. The number of possible unique screen images, states, is astronomically huge, far more than grains of sand on all the beaches in the world. Building a Q table for Atari would require an impossible amount of memory and computation. Our program would crash long before it could store even a fraction of the possibilities. This is the crucial problem that prevented Q learning from being applied to complex, realistic scenarios like video games with visual input. We need a smarter way to generalize rather than memorize every single situation. This is where deep learning, and thus deep Q networks, comes to the rescue. Instead of a massive, impossible Q table, we use a deep neural network. Think of a neural network as a super smart pattern recognizer. We feed it the raw pixels of the game screen as input. Instead of looking up an exact match in a table, the neural network guesses the Q values for all possible actions directly from the image. It learns to identify patterns, like, if I see an enemy approaching from the left, moving right is a good action. It can generalize to new, unseen screens because it's learned the underlying visual features. For us, this means we're replacing an unfeasible lookup table with a trainable model that can make Intelligent predictions. Training a neural network with just the current moment-to-moment gameplay can be unstable. It's like a student only remembering the last sentence spoken, forgetting everything before it. DQN uses experience replay. The AI stores its past experiences, what it saw, what action it took, what reward it got, and what the next screen looked like, in a large memory buffer. When it's time to learn, instead of just using the very latest experience, it randomly pulls out a batch of past experiences from this memory. This helps the AI learn more effectively by breaking correlations. Game actions are often sequential. Random sampling breaks this sequence, helping the network learn more robustly. Reusing data. It can learn from important past events multiple times. Stabilizing training. It prevents the network from getting too focused on immediate, potentially misleading events. From a developer's perspective, this is like building a smart database of gameplay moments and training our AIs brain by reviewing random snippets from it. Here's another clever trick for stability. Imagine you're trying to hit a moving target, but your aiming mechanism is also constantly changing based on where you think the target will be. It's incredibly hard. In DQN, the neural network tries to predict Q values, and it also uses these predictions to update its own parameters. This can lead to instability. The solution is a target network. We use two identical neural networks. One is the MAN network that's constantly learning and making decisions, and the other is a target network that is a slightly older, frozen copy of the main network. The main network learns by trying to match the Q values predicted by this stable, older target network. Periodically, we update the target network to match the main network. This provides a stable goal for the main network to learn towards, making the training process much more robust. So, let's put it all together. The AI observes the game screen state. It feeds these pixels into its deep Q network, which predicts the quality Q values of all possible actions. The AI chooses the action with the highest predicted Q value. It performs the action, gets a reward or penalty, and sees the new game screen. This experience state, action, reward, next state is stored in its memory buffer. Experience replay. Periodically, it samples random experiences from this buffer and uses them to train its deep Q network, aiming to match the stable predictions from its target network over millions of game frames. Through this continuous loop of playing, remembering, and learning from stable goals, the deep Q network learns complex strategies entirely on its own, eventually playing Atari games at an expert, often superhuman, level. As developers, we've essentially built a system that learns to be an expert gamer from scratch. Thanks for watching. If you found this helpful, make sure to subscribe to our channel and hit the like button.